Hello. Looks like I've been given a thumbs up, so it's probably time to start. Okay, so my name's Matthew Revell, and thanks very much for joining me here on the final talk of the day. I know you're all probably waiting for the party, but I'll try and keep it light. And yeah, so NoSQL's biggest lie: SQL never went away. That's the title of the topic, and I'm Matthew Revell. I work for a company called Couchbase. And we do database type things, as you might expect. I want to start off by introducing you to something I bought recently, and it's a Bosch Toaster. As you can see, it's quite a funky colour, and there are a few things that are interesting, I think, for this particular topic. One is it's got two slots, so if one slot goes wrong, I can carry on making toast in the other slot. It's neither favours input or output. It's equally good at putting bread in and getting toast out. Despite it being a Bosch, which is slightly fancy in the non-fancy world, it's commodity hardware. I don't think there's any kind of custom fabrication going on here. It's just standard off the shelf parts. If I want to make a lot of toast, I can make a cluster of toasters and have many of them, and that's perhaps a dream I can hold on to there of having many toasters. But perhaps most interestingly of all, it's not a SQL-powered toaster. I can carry on as I want without having to write a single line of capitalized SQL. And well, why is that interesting? And what's that got to do with databases, or SQL indeed? The term NoSQL is kind of a silly term that uses one thing to group together a whole load of disparate databases. And actually that one thing that we're using to group those together is increasingly inaccurate, as I'm going to show. So I think probably what we want to call them is non-relational databases, because that is the thing that they've got in common. And within the parameters of non-relational is basically everything in the world that isn't relational. So I want to go through primarily the different ways in which we query those databases, because the data model tends to impact, at the very least, if not dictate, the way that we query the data. So let's have a look at a quick history of how we store data. In the spirit of not using relational to be our only definition of a database, this is data. This is about 5,000 years old. It's one of the first examples of human writing. It's from Mesopotamia, which is modern day Iraq, roughly, I believe. And our best guess, or the best guess of archaeologists, is that they used it to store data about, or information rather, about agriculture and taxation and things like that. So very similar to the sort of things we put into Oracle these days. And I was quite keen on proving that idea. So I had a look around. I popped it into Google Translate, and as you can see, it's all about rice and things like that. So yeah, moving on. This is also data. This is a Jacquard loom. It's the first form of reproducible instructions that can be given to an entirely different machine somewhere else, that so long as it sticks to the spec, will do the same things that the creator intended. And it's only in 1960-ish that we get the first commercial electronic database, and that was IBM working with American Airlines to reduce booking a flight from about 90 minutes of going through manual books and filling things out and then sending off a telex and so on, to having a system that would bring it down to about 90 seconds of going through, by today's standards, a relatively slow database. And the Sabre system was not a relational database. It was what we would probably call a file system now. It was really just a set of hierarchical records that were linked to each other, and it made a huge difference and gave American Airlines for a while a competitive advantage, and then was rolled out everywhere. And Sabre as a company still exists. They're independent of IBM and American Airlines now, but they still exist, and just as an aside, they use Couchbase. So the data model determines the query pattern. What do I mean by that? It's fairly straightforward, but let me provide some ideas to back it up. So the first databases as we would know them now were the hierarchical databases, also called the go-to statement of databases, because effectively you have a route at the top, and you can go through and you can follow a very specific pattern, and you say, is this the thing I want? No. Okay, go to the next thing. Is this the thing I want? No. Okay, go to the next thing. Is that the thing I want? Yes. And so, a modern day example of that would be the Windows registry. Even looking at it now, you can see that it's hierarchical, and then there's some data in there, and it makes its way through. In a more perhaps enterprisey scale example would be IBM's IMS, which is used still in banking and other industries, and it's still ticking along, but it's much less perhaps the option that it was in the early 60s. And the DOM is another hierarchical database where you have this XML representation of a set of data. So looking at it, querying that data, like I say, is a case of you start at the top. In this case, we have the CEO, and you work your way through until you get the record that you're looking for. So somewhat that is really about you are providing instructions in as much as telling the database what to do in order to get the data you want, rather than a declarative query where you're saying, give me this data, and I don't care about the detail of how you work it out. Moving on to the mid-60s, and you have the network database, which was introduced the radical concept of going sideways as well as up and down. And this came out of the Codicil working group, who, amongst other things, created COBOL. And there's Admiral Grace Hopper in the front, and various other people who came forward with this at the time revolutionary way of doing things. And so in a network database, you might have employee records, and you can kind of think of it as a big linked list. So you then have a link on to sibling records, but you can also have the hierarchical view as well. And again, you're still working your way through a set of data by saying, is this the thing I want? Yes, no. You have a little bit more control and a little bit more insight into the data because you can follow those linked list type things, but you're still navigating through the data rather than putting the work onto the database itself. And of course, the way of querying that was primarily through COBOL, which was fine at the time, but it's somewhat less nuanced and easy to work with than what we would be experiencing today. Then 1970 comes around, and E.F. Codd, working at IBM, comes out with the relational paper and proposes the database that we're primarily using now, or the data model, a little bit later, and some of his colleagues come out with SQL as a way of querying that. And so for the first time, we have a declarative data query language. And that is a function of the data model itself, because without the data model that Codd proposed, it would be much harder to query it in the way that we do. And then we come to the late 80s, early 90s, and we have object databases following the object-oriented revolution. And people said, why are we flattening everything into tables when we've got these lovely nested objects? And the world kind of didn't really care and carried on with relational databases because they offered enough benefits to not overcome the disadvantages. But then 2005 comes, and we have the beginning of something of a Cambrian explosion of database options. And the relational database brought around its dominance from perhaps the late 80s through to, well, now clearly. But it was really the default way that we've stored data. On a hobbyist basis, you would fire up MySQL. In the enterprise, you would have DB2 or Oracle or whatever, and that was the way we did things. And I've spoken to lots of people who say, who understand the world only through the framework of the relational database. But the NoSQL database movement brought around lots of old ideas and said, well, we're now perhaps solving for different problems. You know, if we have a website or a mobile application that has many thousands of users concurrently, and we can't really predict how many of them there'll be or when they'll come, or you know, perhaps it's no longer acceptable to have an animated GIF of someone digging a road when we want to do some maintenance on a web application. You know, we are solving for different things, so it's okay to make different trade-offs. So we might give up transactions, but we might get in place of that, we might get greater horizontal scalability. So what are those types of database that are coming around 2005? Well, like I say, they're going back to old things. So key value stores. The key is the important part. That's your only route into the data. The value can be anything. It's opaque to the database. So it could be a string. It could be a JSON document. It could be an animated GIF. It could be anything. The database itself doesn't really care. And that's okay. That's really useful for caching situations, or you know, where you have something very simple like in Chrome, for example, it uses level DB to store various different bits of configuration and other information about how you use your browser. But generally speaking, we want some more insight into our data, and with the key value store, your query is, here's the key, give me back the data. So if you don't have that route into your data of the key, then you might be stuck. So document databases build on that by giving us additional indexability and additional query of the data that's inside the value. So generally speaking, we're talking about JSON databases. There are XML databases like MapReduce, but mostly with the current group of open source NoSQL databases, we're looking at JSON. And you might have something like this where you have a user profile, and you can create indexes on individual parts of that JSON document and then query them and make updates to individual parts of the database rather than, you know, storing an entirely new document just to add one more line to the JSON. And then you start to be able to, like I say, run indexes, so you could have all of the people who work from the London office and all the people who work in a particular team, and then you might be able to find the cross-section of those. And so it gives you some form of queryability. I'm just going to move this. But it doesn't give you the, it doesn't necessarily give you the queryability you'd get from a relational database, because again, you're making a trade-off. You're hoping that the things you get from a document database, which would be easy distributability of that data across a cluster, you know, a lack of schemas, or at least enforced schema by the database, so you can be very flexible in what you store. You're hoping that those things trade off enough to give up the transactions and the great queryability that a relational database would give you. And then there's column databases, which are great for time series data and things like that. And graph databases, which, if you're not familiar with this very pixelated map of Königsberg, was created by the mathematician Euler, who lived in Königsberg, and the legend says that he wanted to work out if the Kaiser could visit all of Königsberg without crossing each bridge more than once. The answer was he couldn't, but he came up with a branch of mathematics to solve that problem. And really, the whole thing about graph databases is that you have a network of nodes. Your data points are, you know, perhaps people, and it's the connections between those nodes in the graph that are the important thing. It's not necessarily the data itself. So you can do things like, a common use case for a graph database would be a dating site where you can connect people together based on their likes and things like that, or maybe routing parcels or mail across the most efficient distribution route, which happens, you know, a parcel company might get a parcel in, and they'll very quickly scan the address, and within split seconds work out which truck it should go into for the most efficient route, because they'll have worked out with the graph database. So, okay, lots of different database types, and there are many more other NoSQL database types as well, but these tend to be the four common ones in the current open source NoSQL movement, let's say. But the important thing is that context is everything. So you choose that database based on the workload you're going to put onto it. So rather than just throwing everything into a relational database, we're now, as Martin Fowler calls it, we're going for a world of polyglot persistence, where we have different data stores for different use cases, and it's all about making the trade-off that matches that particular use case. So we might want a cached key value store for mainframe offload, because all of the actual interesting stuff is happening on the mainframe, but we're actually just trying to save some expensive mainframe cycles, and we're throwing it into commodity hardware with a key value store. Or we might want the scalability that something based around the Dynamo paper's idea of scaling might give us, which would be very easy horizontal scalability. Or we might want the queryability that something like a graph database would give us. But they all have their own trade-offs. So the graph database won't scale very well. The Dynamo-like big table like Cassandra won't give you strong consistency. So you'll have to sometimes resolve conflicts, because you one of the trade-offs you make for that scalability is that you have many masters of the same record, and you can write into any of them at once. So all those differences in data model translate into different trade-offs, and also translate into different ways of querying. So one of the first NoSQL query methods was for the NoSQL database designers to say, well, actually, this is your problem. I couldn't find a picture of a ostrich burying its head in the sand, because they don't do that, but this is an ostrich. Effectively, they were saying, well, we're giving you all these great things like scalability and uptime and stuff like that, so query, that's your problem. People found ways of getting around that. One of them was creating manual secondary indexes. So, you have a set of documents. You might have a London document where you just list the key names of the people from London, for example. And then you can iterate through that manually in your application layer. And that's a way around it. It works, but it puts all that burden on you as the application developer, rather than having the database layer do the things that you might expect it would do. Rich Hickey refers to the difference between basically a file system and a database. A database gives you query, a file system is just a place where you put things. So you could then call up one of those and get the result back. MapReduce was an early contender from, brought over from the big data world. So MapReduce in something like CouchDB or Couchbase and other databases would allow you to either do the batch kind of stuff that we'd expect from Hadoop, or in the case of CouchDB and that family of databases, give you a near real-time set of secondary indexes that were automatically generated, or give you aggregation of data. So in this case, we could write a little bit of JavaScript and get back that index of people again, but this time it's generated automatically. The one thing we're missing, though, is that we're going back to that world of kind of navigating through the data, or basically procedural programming for databases, where we're saying, do this, did that work? No, do this instead. And okay, maybe that trade-off is worth making sometimes. But really, we want declarative query for being able to mentally put the burden of the how somewhere else, but also to give us that richer query, that ad hoc query that we expect from our databases now. So in the NoSQL world, I'd say there are broadly three schools of declarative query coming about. There are forms that are specific to a particular database and have been created for that data model and are kind of a new option, but you will only find it in one particular database. Then there are attempts at industry-wide forms of declarative query, where people are saying, let's all try and do this instead of having our own proprietary systems, or not necessarily proprietary, but yeah. And then there are SQL derivatives. So let's have a look at a database-specific one. MongoDB has its own query language. It's really about chaining methods together, and it's straightforward and quite simple. And it lets you do things like this. So if you want to find everyone whose office is listed as London, well, you just would do something like db.staff.find office London. If you want to do an insert, then again, it's like I say, it's fairly simple. You put the database name, the collection name, and then the command you want to do against that particular collection. So you can see that it's straightforward. It gives you declarative query, but it's something new to learn. Then one of those bold new options of, well, let's all work together and create something great for the industry would be Jsoniq, which is comes out of the X-Query world. It was basically the people of the X-Query committee said, well, what would happen if we put together everything that's great about X-Query and made it available for people who are working with JSON data? You might have opinions on whether X-Query should be brought to a broader audience, but I will leave that for you to decide. So it gives us a declarative query language for JSON. It's functional, and importantly, it's set-based. So it's not tuple-based, it's set-based. So you're automatically working with the assumption that you're going to be dealing with nested data and JSON-shaped data. So what does Jsoniq look like? To me, I can't get away from the idea that it looks a bit like Pascal, but yeah, so you can do things like, here what we're doing is we're getting everyone from the staff collection who has a service of more than 2 years, and then we're combining their last name and first name into a single name and grouping them by office, ordering by how long they worked for it, and then returning that. So in some ways, it almost looks like someone's really trying hard to make it not look like SQL, but if you strip away some of the curly braces, we are talking about something that's very SQL-like. You can even do joins with it. So here is an example of finding all of the movies in which different Star Trek captains appear. And what you can see again is that you're bringing in you're bringing in a for loop and a try-catch situation. So you've almost kind of got error handling in your declarative query. So to me it feels a bit less declarative than it might do. But it gives you a join across two different sets of documents. And there's a lot of work gone into this, and a lot of people really believe in it. Unfortunately, no database vendors believe in it. So it's kind of still a bit academic right now. But it's out there. And then there's the SQL set of query languages for NoSQL databases. So why SQL? Well, the first thing is the tooling. The other thing is it's really familiar. If you have ever done anything at all with writing software primarily for web stuff, as well as anywhere else, then you'll have touched SQL at some point in your life. Even if it's fighting with PHP and MySQL or something much bigger, then you've touched SQL. And so many different NoSQL databases now are adopting SQL-like languages. Probably the first one to do this was Cassandra. And they have CQL. So CQL, it really looks like SQL. It brings schema back into the equation because of the column model for of storing data requires that you think up front about how you're going to store it and the shape of it. It doesn't give you joins. It doesn't give you group bys because, again, the data model is dictating the ordering and things like that. But it looks very familiar. You create a table by creating a table, and you specify things like a primary key. Well, what is a primary key? That's the key that's hashed and decides on the distribution of your data. And then you add some more keys which will decide on how it's ordered on disk. So this is a really important thing. This is declarative, but it's perhaps not ad hoc in that you have to think up front about how you're storing the data on disk, because that will then dictate the efficiency of the querying that you do. So if we have a look at an example I've borrowed from a blog on Planet Cassandra about SQL, would be putting in Tom Clancy books into Cassandra. So you would insert them using CQL like this, and again, this looks familiar. and the result would be something like this. But this is an abstraction to make it feel more comfortable and more familiar, because actually how it's stored on disk is more like this. And the important thing here is that year key, and you can see we've only got a couple of examples there, but you can see that we're storing it in descending order. So that means that we can very efficiently do a range query across that based on year in descending order. But if we want to do anything else, then we have to rethink the way we're doing things, because it could become very inefficient or even impossible. So we want to find all of those books by Tom Clancy that are published after or in 1993. We write something like that. Again, it feels very familiar within the constraints of the data model, and it might give us back boink, something like that. So you come down, and the reason it's so efficient at doing this kind of query is that it's all stored in order already. So it comes down, and the minute or the millisecond that it hits something that's less than 1993 it'll stop. And that's fine, because it knows, you know as well, that anything after that, because of the order it's stored in, won't match your criteria. But then if you wanted to do it by some other order, you might be in trouble. So it's not an ad hoc query language. But it is, if you set yourself up and do that forethought and so on, it is a great way of querying that type of data. But a lot of what certainly people working with the web and mobile are dealing with is JSON. It's not columns to sorted data. I always have to apologize for this slide. JSON might seem as far away from the relational model as you can think of it, really. But actually, if you allow yourself to forget about normalization, which I agree is, a core tenet of why the relational model works, but if you just kind of forget about that for a minute, then JSON data starts to feel a bit more like relational data. So what would we need from SQL for it to work with JSON data? Well, you have to accept that the data you're working with is semi-structured. From one document to another, it could have an entirely different schema. And the database cannot enforce a schema on it, because then it wouldn't be the flexible data format that we want. I mean, I guess you could have a rigid schema enforced by the database for a JSON data store, but nobody's tried it as far as I know. It's going to be heterogeneous, so not only will it change shape, but you could easily have different data types in the same places, or even for the same key names inside there. And we probably want JSON in, JSON out. We probably don't want to pull rows and columns out of our JSON database. So we need, like I say, we need to accept that data's nested, data might be missing, so it's going to be changing in shape. It will be denormalized in all the forms of normalization, and you're going to want joins, but they're probably going to work somewhat differently. And your SQL-like language for JSON will need to abstract away those differences and make it as pain-free as possible. Some people at the University of Berkeley, California, were thinking about this. And if you do a search for SQL++ paper, you'll get, it's relatively short for an academic paper. It's an interesting read, though. You'll see that they've put a lot of thought into how they would apply SQL to JSON data. And they came up with these two things, SQL++ and JSON++. JSON++ is a minor and not necessarily necessary change to JSON, but SQL++ takes the very familiar SQL language and adds a few bits. So one of those things is that, it can handle missing data gracefully, and it can query inside nested data. Now, I know that SQL 2003 has some nested capabilities, but this is working more around ANSI 92 SQL. So it's about dealing with those objects and arrays that you can find nested inside JSON. And it allows for joins between documents. Now, right now, SQL++ is pretty much, again, an academic thing. they have an implementation which isn't production ready or battle tested. It's just there to have a go. But the open source Couchbase project does have an implementation of most of the SQL++ paper. And it's called NoSQL, which stands for Non-First Form Query Language, because we all like acronyms, sorry. So right now, this is an open standard. It could be implemented on any JSON database, but right now it's available for Couchbase. And it came in Couchbase Server 4.0, which is a distributed document database with built-in caching. So that's kind of what you need to know to understand what comes next. Yeah, and it offers a few different ways of accessing the data in there, but the most important thing is that it's a JSON database that has NoSQL. So what does NoSQL do? Well, it implements pretty much what I spoke about with SQL++. It deals with the nested data, it gracefully handles missing data, and it does joins. So let's have a look at that document I showed you very briefly earlier, which was my profile in this team. So it shows a few bits of personal information about me and some conferences that I've been to. So to find everyone who works out of the Couchbase London office, I would write something like that. No surprises there, it looks very familiar. And if I do that, then I get a bunch of JSON data back. And there's some metadata around it, but the actual results data is what I asked for. I asked for the email addresses of everyone from the London office, and I get that back. It can also deal with the arrays that are in there. So my list of conferences was an array, and so this is where we're first dealing with nested data. So I want to find all of the names of all of the conferences that people in that database are going to. So I'd write that, and I would get something back like this. Now, you can see a couple of things here that are interesting. One is that you have some blank results, because not every document has that conferences array in there. And the other is that we've got some duplication, because duplication's going to happen in JSON. So how do we get rid of that? Well, it's pretty much what you think. You do a select distinct, and then you say something which you might not expect from a SQL-like language, which is you say, well, just only give me back the documents where conferences is not missing. And then we lose our duplication and we lose the empty documents. So there we go, we get back just the list of what we wanted. And then we can say, well, who's going to a particular conference? So we say, well, we can then dive into one of the arrays and say, if any event in that conferences array has a name that satisfies this, then give it back to me. Then we can find the people who are going to that conference, which was James and Martin. And as you'd expect, it does mutations. So you can delete data and insert data, or that's pretty much it, isn't it? But yeah. So looking at a slightly bigger travel set, I want to show you the next step, which is to do joins in data. So Couchbase comes with a bunch of travel data, things like airports and airlines and the routes between airports and the equipment that they use. And that's basically 33,000 documents where you can start playing around with this stuff. So what are joins in the context of a NoSQL database? And one of the things that has kind of defined NoSQL databases is that you put data in, and when you pull it out again, no matter how much clever query you do, you're just getting back the same data that you put in. You can perhaps miss some of it out, but you're not really combining data together from different sources. So with the join, we want to take different documents and combine the data that's inside them to give us exactly the result we want to, so that we're not having to do that processing on the application layer. So if we imagine that airline data and so on as tables in a relational database, we might have something like this. No real surprises there. In JSON, it would look something more like this. So we'd have a document for an airline, a document for an airport, and then the route between those. So I've truncated the actual schedule information, but you can see that we've got a nested array of objects, which is really the actual individual flights between those cities operated by that airline. And yeah, so what we can do is we can do a join between some of this information to return something useful that you might want in a real travel application. So I might want the flights that go from one airport to another, and if this is my data set, I might write something like this. So what's really interesting here is that we are doing a lot of work in the last two lines. So in Couchbase and many other NoSQL databases, you don't have the same granularity that you have at the table level. You tend to throw things into buckets, and you could have potentially millions of documents in one bucket. So basically the where clause does a lot more work because you don't have that equivalent level of granularity. So here what we're doing is we're saying where the source airport is Heathrow, the destination is San Francisco, and then we're doing a join across documents. So we're saying in those documents there'll be an airline ID, and what I want you to do then is join in on the other side from documents whose key matches that airline ID. So what happens if we do that? This is where. So I'm going to paste it into the nickel REPL and get an error, which is great. I actually closed down Couchbase because this isn't a problem on the server, but it was killing my battery. So that's why I didn't have it running. I'm not an unprofessional person, a bad presenter. No. So let's try that again. All right. So that then gives us back all of the airlines, because we've said, give me back the airline ID and so on, who are running those routes. So now we know that if we want to go from Heathrow to San Francisco, according to this data set, those are our choices. Now, I mentioned that I truncated the actual schedule information, but in there was a whole load of objects describing individual flights. So we want to be able to do something useful with that data. And to do that, we need to unnest that data out there. We need to promote it to the top level to use it in our query. And so what we do here is we still have that source airport and destination airport, and we still have that join so we can pull in the airline information. But what we're going to do is we're going to pull out the schedule information and use that in our query. So it almost becomes like a three-sided join, in that we are using the unnested data within our query. So we're saying LHR to SFO, give me the airline ID as well, airline details as well, based on the key that's inside that document. And then unnest out of it the schedule information, so then we can use that as S, and then say, just give me back the flights are on a Monday, and then order it by the time that they leave. So we try that. You see that we get all of the flights on a Monday, regardless of airline, ordered by time. And so that's something that you might actually use in a real travel app. So you can start to see that we can have that separation of concerns in our JSON data that we saw in the database, but then bring it together using very familiar queries that we can then put into things like JDBC or ODBC, use with various other other tools that would expect something SQL shaped, or just write queries, or use something like Spring Data. So we have the Spring Data Couchbase connector, or use an ODM, or whatever it would be, to now really forget about the fact that the data we're working with is stored in one particular format, but just get that queryability and that familiarity and power that we expect from SQL. So while up until now the entire history of data storage has been that the data model dictates how you can query it, I think we're now at a time where perhaps we can be more choosy and say, well, actually, I like this data model, but I like this other data model's type of query, and bring them together. And that's it, really. That's Nickel. That's one way of working with JSON data and bringing SQL into it. But I do think that we have to drop this name of NoSQL, because increasingly these databases are using something like SQL, if not SQL itself. If you do want to see more, then you can, about Couchbase, and there's our developer portal, developer.couchbase.com. If you want to see more about SQL++, there is the URL. That's why I say you should probably search for SQL++ paper. That's Couchbase forums, and that's about it, really. So thank you very much for your attention, and I hope you've had a great day in Bristol. And let's go and see about finding a job in Bristol. Thanks a lot. Bye.